In this paper, we present a new method, SparseNeRF, distilling depth ranking for few-shot novel view synthesis. Our goal of this task is to synthesize novel views with a limited number of views for training. The inputs are sparse view images. The output are novel views synthesized images in a 3D space. One solution to the few-shot NeRF is to exploit depth information to improve the performance. However, it is difficult and expensive to collect accurate depth maps. As shown in the videos, depth maps predicted by pre-trained single-view depth models are inconsistent in the 3D space. Depth maps from Connect and Z2 are not accurate and stable. Moreover, scale invariant errors are obvious in these depth maps. Motivated by these problems, we consider the robust depth ranking regularization instead of directly supervising NeRFs with depth values. We show the overview of the proposed framework. The proposed SparseNeRF consists of three main components, including reconstructing color, distilling depth ranking, and distilling spatial continuity. In the first part, given 3D points X and their directions D, we use MLP to map X and D into colors C and density sigma. We reconstruct pixel values by blending color and density. We use L2 as the NeRF loss. Then, we consider depth prior distillation. We consider two types of depth maps, including depth maps predicted by pre-trained single-view depth models and depth maps captured by consumer-level sensors. These depth maps are not accurate. Therefore, instead of directly supervising a NeRF with coarse depth priors, we relax hard depth constraints and distill robust local depth ranking from pre-trained depth models to a NeRF such that the depth ranking of a NeRF is consistent with that of the pre-trained depth model. Finally, we further propose a spatial continuity constraint on depth maps such that the NeRF model imitates the spatial continuity of large pre-trained depth models. We collect a new dataset NVSRGBD. The new dataset includes coarse depth maps, captured by Azure Connect, Z2, and iPhone 13 Pro. We study how to exploit these incorrect depth maps to improve few-shot NeRF. We then compare regular NeRF on the new NVSRGB dataset. We first consider the Z2 depth sensor. We compare three methods, including regular NeRF, monocular SDF, and DS-NeRF. Among them, mono SDF is originally designed for surface reconstruction. We implement mono SDF to NeRF. We can see that our SparseNeRF yields better performance for novel view synthesis. We visualize more scenes. We then consider the results of Azure Connect. We visualize more scenes. We compare the new state-of-the-art method regular NeRF on the LLFF dataset. We can see that, for regular NeRF, the geometry of scenes are not fully synthesized. Instead, our SparseNeRF achieves yields better synthesis. We visualize more scenes. We then compare regular NeRF on the DTU dataset. We can see that our SparseNeRF achieves better results for novel view synthesis. We visualize more scenes. We apply the proposed SparseNeRF on iPhone 13 Pro. It shows that the proposed SparseNeRF achieves promising results. We shows another application. The users are asked to click near far depth pairs for depth ranking supervision in a local patch when we do not trust the coarse depth. As we can see, the synthesis view significantly improves with about 30 near far pairs. Note that, in real-world scenes, we only need to refine some local regions instead of the full image. Thank you for watching.